When we look up at the night sky, we see a seemingly static, quiet expanse. But step just outside our solar system, and the environment is teeming with chaotic, blisteringly fast, and violently active cosmic engines. Take our closest interstellar neighbor, Alpha Centauri. It appears to the naked eye as a single, steady point of light, but it is actually a dynamic three-star system. Intense gravitational forces whip planets around their hosts, while the stars themselves eject frequent, violent flares of radiation. Identifying exoplanets in the middle of that chaos, like Proxima Centauri b, requires dissecting the faint light reaching Earth. We rely on spectrographic data captured by enormous ground-based observatories. Massive facilities like these four structures, the Very Large Telescope, allow us to isolate the tiny chemical shifts in starlight. These stars are also moving across the sky at incredible speeds, a trajectory known as proper motion. Barnard's star, a dim red dwarf, is currently hurtling toward our solar system at over 100 kilometers per second. Even our nearest celestial neighbors are aggressive, dynamic reactors. They're capable of stripping away atmospheres and sterilizing or freezing the worlds caught in their gravitational grip. The space between stars is often perceived as an empty vacuum, but our solar system is currently traversing the local interstellar cloud, a 30-light-year-wide region of hot, rarefied hydrogen. We know this because physical debris from this gas has reached Earth's surface. By drilling deep into the Antarctic ice, researchers have uncovered distinct isotopes of interstellar iron that originated far beyond our solar system and drifted down through the atmosphere. This local cloud is a small fragment of a larger structure called the local bubble. Mapping out our position in this diagram reveals a 300-light-year-wide cavity. This void was carved out by successive supernova explosions detonating millions of years ago, pushing a dense wall of gas outward. Our immediate cosmic environment is a crowded debris field, filled with the radiation and gas left over from detonated stars. Further out, the extreme physics of the Milky Way force planetary materials into configurations that defy Earthbound logic. On the exoplanet Gliese 1214b, water is not just a surface feature, it makes up the vast majority of the planet's entire mass. This diagram illustrates what that volume of liquid does to a planet's structure. With ocean depths exceeding 100 kilometers, the weight of the water creates an immense amount of physical pressure pressing down on the core. That pressure crushes the lowest liquid layers into a thick mantle of Ice 7. This exotic modification of water remains solid even at searingly high temperatures, forming a massive cryosphere that settles on the ocean floor. Material states are also pushed to extremes on the lava planet K2141b. Gravitational forces lock one side of the planet permanently facing its star, heating the day side enough to evaporate rocks into the atmosphere. Supersonic winds carry that rock vapor to the cooler night side, where it precipitates as fiery rain and flows back into a churning magma ocean. These planets function as volatile chemical reactors, their entire compositions dictated by the gravitational and thermal forces of their host stars. Stars operate in complex, often dizzying arrangements. The Castor system is a gravitational dance of 6 separate stars, securely bound together and moving around a common center of mass. But stellar bodies also face catastrophic life cycles. The red giant CW Leonis is nearing the end of its life, suffering from irregular pulsations as its internal fuel depletes and gravity struggles against thermal expansion. As the star runs out of hydrogen, its outer layers swell to monstrous proportions. If CW Leonis were placed in the center of our solar system, its expansion would consume every planet, all the way out to the orbit of Mars. A star's death is a violent expansion that inevitably annihilates the planetary systems it once fostered. The remnants of these collapses are often lethally hostile. Pulsars are ultra-dense neutron stars, spinning thousands of times every minute, sweeping intense beams of electromagnetic radiation across space, and bathing any nearby planets in deadly energy. In even more massive collapses, stars transform into black holes. In the binary system A0620-00, the black hole's gravity physically deforms its neighboring star, stretching it toward the center and stripping away its outer layers. That stolen stellar gas spirals inward, creating an accretion disk. Immense friction superheats the gas into a brilliantly glowing ring before it crosses the event horizon and is consumed. These violent collapses facilitate a larger cycle. The shock waves and extreme temperatures at these epicenters forge heavy elements like gold and uranium, scattering the raw materials required to build future generations of stars and planets. Pulling back from these individual systems reveals that this chaos is tightly organized. The Milky Way functions as a single unified structure, forged over 13 billion years. The anchor of this entire structure is Sagittarius A star. This image captures the radio signature of the supermassive black hole at our galaxy center, a gravitational titan with the mass of 4 million suns. The gravitational environment near this core is so intense that nearby stars are whipped along their orbits at significant fractions of the speed of light. By observing the distribution of billions of stars around that core, astronomers like Edwin Hubble established our galaxy's macro shape, classifying it as a barred spiral. The anatomy of the galaxy is precisely layered: a dense central bulge, star-forging spiral arms, and an expansive outer halo that reaches hundreds of thousands of light-years into space. Calculations of the Milky Way's rotational speed reveal a massive physical discrepancy. Every gas cloud, star, and black hole we can observe only accounts for roughly 10% of the gravity required to hold the galaxy together. The remaining 90% is dark matter. This diagram illustrates how the visible galaxy is actually embedded within an immense spherical web of this invisible material, which provides the gravitational scaffolding that dictates the physics of the entire system. The Milky Way functions as an evolving system of matter and energy, shaped by forces we are only beginning to map. Within this structure, our solar system is a single passenger, riding along the Orion arm for a brief moment in galactic time.